So we have a great talk tonight. Miles Traer is a Stanford geoscientist. This is actually his second appearance here at the Interval. I don't know if anyone was here for our heroic Antarctic event that we had. All right. Last year it was a collaboration with the folks at Odd Salon, our good friends. I think we got a couple Odd Salon folks here tonight. Yes. They're going to be noisy tonight, but it's a good thing. They're another great local speaking series, and actually would encourage you to check them out as well. And Miles is also the co-founder of the Generation Anthropocene podcast, and we'll talk to him a little bit that hopefully in Q&A we'll talk a little bit about that and about the geology of the Game of Thrones world and some other fantastic things that he does with his science skills. So we have that to look forward to. But right now we're going to start right here and deep below where we are right now. The Geologic Reveal begins now. A round of applause for Miles Traer.
Thanks, Michael. Hello. Mic check, mic check. Yay! Thanks for the intro, Michael, and thanks to the Interval for having me here. Very excited. I am Miles Traer. I am a geological data scientist at Stanford University, and tonight I wanted to talk with you about the Geological Reveal. There is a natural language embedded in our planet, and it's a beautiful language. It's a language of ecology. It's a language of climate change. It's a language of natural disasters, of earthquakes and volcanoes. It's a language of biology, evolution, and humans. We learn how to read this language so that we can decipher the relationships between these staggeringly complex systems. In fact, these systems are often so complex that the language often sounds like My job is to translate that. And to make that translation, I use the tools of data science, computational physics, and geology. Specifically, I look at planetary surface evolution. And the fancy name for what I do is called computational geomorphology. It basically says that I study the physical processes that create and transform the land's surface. I then take those processes and translate them into the language of physics. This is what modern geology looks like. The processes that I study can be tectonic. They can be huge forces that slam continents together and rip them apart. They can be rivers that slowly erode down the mountains formed in those continental collisions and transport sediment from the highlands to the lowlands and deposit it all places in between. Or those processes can increasingly be us humans, who today dig up and transport more sand, rock, and dirt than all of the world's rivers combined. If that last fact didn't make it clear, we have a complicated relationship with the natural world. It's one that's gone back a long, long time, but even that word relationship, which I realize I used in the title of my talk, that word relationship is problematic. It's a little bit misleading. We don't have a relationship with the natural world. That would somehow imply that we're separate from the natural world, and we're not. Otherwise, we wouldn't be able to read our history in the rock record. This is exactly why future geologists will be able to dig back through the rock layers and read our relationship with the natural world today. So that's what I wanted to do tonight, is take a look at that natural relationship. And I thought I'd focus in on the Bay Area. And I thought we'd do that for two basic reasons. One, we're all here. We're in the Bay Area. And two, if I tried to cover our relationship to the planet, we'd be here a while. In fact, we might be here until the long now's 10,000-year clock stopped spinning. So one of the challenges in asking a geoscientist to talk about the natural history of the Bay Area is that to a geoscientist, pretty much everything is natural history. And that goes for everything from contemporary climate change to hundreds of millions of years ago when all of the continents slammed together to form the supercontinent of Pangaea, to billions of years ago when bacteria first learned how to photosynthesize and first breathed oxygen into our atmosphere, to that elongated moment 4.5 billion years ago when a collection of dust and debris slowly formed a ball that we call Earth. So rather than start today and just go back millions of years aimlessly, I thought I'd try to focus in on some of the major reasons Homo sapiens, humans, first came to the Bay Area at all and eventually built San Francisco. And I'll suggest that all of those reasons owe themselves to geology. So here are my greatly oversimplified reasons humans first came to the Bay Area. 1, there was a ton of stuff to eat. 2, the Bay was a natural harbor that provided sanctuary from the elements. And 3, gold. So let's start with that first one. The historian Alfred Crosby wrote, "It is crudely true that if man's caloric intake is sufficient, he will somehow stagger to maturity, and he will reproduce." Or, as I've paraphrased it, if bacon, then sexy time. So what was there for the first humans to eat? Where were they getting their calories from? Well, chances are whatever they were eating, it wasn't coming from trees. And that's because before the Europeans showed up and brought all of their trees with them, the peninsula looked like this. It was covered in huge sand dunes that themselves were covered in shrubs and grasses and these beautiful wildflowers. And there were a couple of native trees. There were oak trees and the California buckeye, but the acorns from the oak trees weren't particularly delicious or nutritious unless you ground them up and cooked them for a really long time. And the seeds from the California buckeye were toxic. So I think it's safe to say their calories were coming from elsewhere. Among the larger animals that hung out on the peninsula were deer, and they were delicious. But they also tended to hang out with, bears and mountain lions, which meant that human hunters had to compete with several hundred pounds of claws and teeth and So that got kind of dicey. But fortunately for humans, there was seafood. And seafood had 2 distinct advantages over dealing with the bears and the mountain lions. It was A, abundant, and B, far less likely to eat you. Nestled into the shoreline were all of these bays and salt marshes that we can read in previous maps or digging down through the bay muds. And these bays and salt marshes were home to countless different kinds of shellfish and regular fish, which themselves attracted all sorts of huge birds and adorable sea otters with their tendency of holding hands while they sleep so they don't float away. There were also millions of salmon that swam through the bay and up the freshwater rivers to spawn. And if you remember those toxic California buckeye seeds, early Native American tribes would use those toxins to, quote, stupefy the fish, unquote, which made catching them way easier. So why is it that so many different plants and animals found such a comfortable home here in the Bay Area? Well, the answer is, of course, geology. So the Sierra Nevada mountains Look, I have different labels for my maps. So the Sierra Nevada mountains are to the east of us. And there are a lot of rivers that drain off of those mountains into the Central Valley. And in California, something strange happens in that two of the largest river systems, the San Joaquin in the south and the Sacramento in the north, hit the Coast Range and converge. Most rivers, as they approach the ocean, tend to splay out into these giant fans, and those fans themselves will tend to jump from one location to the next. I have some experience researching this. And you can read that changing pattern in the rock record. But here in California, those two huge river systems are funneled through a narrow mile-wide gap in the mountains, the Golden Gate. San Francisco Bay is itself a giant estuary that drains something like 40% of all of the land in California. Which means that us here in the Bay Area, we get a lot of California's fresh water converging on this geographically small area. And that's really important because estuaries are basically the nurseries of the natural world. You get all of this fresh water and salt water mixing together, which creates this whole range of environments for all of these different species to thrive in. All of these species that we find tasty. So, if it is crudely true that if man's caloric intake is sufficient, he will somehow stagger to maturity and he will reproduce, then we owe a human presence in the Bay Area to the estuary, which itself was created by the geology. All right, let's move on to that second reason now, and let's fast forward to Europeans. Europeans first came to the Bay Area primarily because it was a natural harbor. And our early maps of the peninsula here show that there were a lot of smaller bays that were tucked into the coastline where ships could safely drop anchor. There was Yerba Buena Cove, there was Mission Bay, and where we are right now in the marina. Humans later filled in a lot of those bays with sand and rubble and debris, often just to keep their houses from sinking into the marsh. But where did those bays come from? Actually, before we get to that, this red outline that I'm showing here is the modern San Francisco Bay shoreline. And this map is from, I think, the mid-1800s. And so you can see how dramatically we've already affected the physical coastline, how dramatically we've already affected the natural environment just in 150 years. So where did that original topography, where did those original bays come from? And in fact, where did the bay come from? Well, the answer is, of course, geology, but not in the way you might think. The presence of the bay itself owes less to tectonic forces and more to ice ages. And that's because for most of its existence, the San Francisco Bay was actually a dry inland valley. Somewhere around 20,000 years ago, Earth was just about to leave the last ice age. And so much of Earth's water was frozen into ice out at the poles that sea level was way lower than it is today. In fact, the San Francisco shoreline would have been about 30 miles to the west of us. The Farallon Islands, which on a good, clear day you can see from San Francisco, which are now a marine sanctuary where you can swim with great white sharks, were once just hills on a vast dry plain. A river cut across the slope, exiting the Golden Gate and entering the Pacific Ocean just south of the Farallons. And at this time, you could have walked from Oakland to San Francisco without getting your feet wet. As you walked through that inland valley, you would have walked through groves of redwood trees and would have had to tiptoe past woolly mammoths. We know this because we found redwoods and mammoths in the bay muds. These are early geologists, by the way. Then around 18,000 years ago, something happened. Climate began to change. Things began to warm up very slowly, much slower than it is now. And as the climate began to warm, sea level began to rise. Sea level crept inland, and it crept all the way up to the Golden Gate, before it eventually flooded the entire inland valley and created modern San Francisco Bay around 6,000 years ago. Ever since that time, the shape of the bay has constantly transformed, partly due to sort of natural erosion processes, but also a lot because of us. We filled in a lot of those smaller bays. We've built islands, and we've totally changed the sedimentation processes flowing into the bay with agriculture in the Central Valley. We've dramatically changed the shape of the bay. And one of the most dramatic changes actually started in the California Gold Rush. During the California Gold Rush, geologists estimate that we dug up something like 8 times the amount of sand and rock than we did building the entire Panama Canal. And we dumped all of that sediment into the rivers. That sediment found its way back to the Bay Area, and that sand and mud totally changed the coastline. But it wasn't just that one physical change that we can read from the rock record, because mixed in with all of those sands and muds were chemical traces, things like mercury that we use to process the gold ore, that provide a marker of how we were interacting with the physical world at that time. Excuse me. So the gold rush had a huge impact on the Bay Area and had a huge impact on our relationship with the natural world. And of course, speaking of the gold rush, let's talk about that gold. So as I was preparing this talk, I began to write down a description, a 100% accurate description of the geochemical process of gold ore deposition. And it's important that you know that this is a 100% accurate description, because it's also inappropriate. And I guarantee after I'm done saying it, you'll never look at a geologist the same way. Gold is typically erupted from deep beneath the earth through narrow slits on the ocean floor. And then the dry continental crust begins to grind up against the moist oceanic crust. And as the two grind up against each other, there's a lot of friction and things get really hot. And then the gold melts and gets pushed deep into thick veins of quartz that get uplifted during the Sierra Nevada orogeny and eventually become the California lode. Geology. Let's leave Barry up there. So the same tectonic forces that created and deposited the gold here in California are also responsible for creating most of California. The Sierra Nevada mountains popped up around 40 to 60 million years ago, and at the time, everything to the west of them was buried under a shallow ocean. And also at this time, there was a smaller tectonic plate called the Juan de Fuca plate that was smashed in between the Pacific plate and the North American continent. And as the Pacific plate and North American continent began to collide in with each other, the Juan de Fuca plate got smushed underneath North America, what we call subduction. And as it was subducted, the top layers of the plate got scraped off and eventually accreted onto the side of the North American continent. Those huge forces of the continental collision also took that central valley buried under the shallow ocean and lifted it up above sea level and eventually created the land that we call California. When you look at a geologic map like this, you'll see a lot of very pretty colors. And it's important to note that those colors don't really represent different types of rock. They represent layers of geologic time. When we read a geological map like this, it's a story of big events passing through history. And in this case, a lot of that history, a lot of that natural history happened before humans ever showed up on the evolutionary tree. But it's these same forces that created the gold, that created the state itself, that created the fertile soil, that ended up leading to humans playing such a large role here in the Bay Area. So up until now, when we've read the rock record, we've seen shallow oceans and we've seen ancient tectonic plates. We've traveled from the ocean floor to dry inland valleys, to sand dunes, to salt marshes. We've walked with woolly mammoths, swam with adorable yet bastardly sea otters, and we've eaten the salmon stupefied by the buckeye seeds. In short, we've seen San Francisco's nature change over millions of years. And most of those changes have been physical, and certainly our imprint has been largely physical. To a geoscientist, I often look for those physical imprints because they're easier to find. Not easy, but easier. But they're not the only remnants that get left in the rock record. They're not the only things that get left there. Ideas are preserved in the rock record as well. And to see how our ideas end up in the rock record, we're going to go from the gold rush to 1906. In April of 1906, two events transpired that forever changed the way geoscientists viewed the Earth. We proved the existence of ghosts using photography. And we found out that lunatics do not, in fact, require toupees. These are both real. So the reason I wanted to start with these two examples for 1906 was mostly jokes, but also to help us travel back in time to 1906 and the types of scientific questions being asked back then. These two rather ridiculous examples aside, this was a time when Harry Houdini was waging a one-man war against seances and mystics. Nikola Tesla's alternating electric current, which all of you use in your homes, was brand new and barely being used in major cities for lighting. And Guglielmo Marconi's long-distance wireless telegraph was state-of-the-art technology for sending messages, and it was very expensive and really only available to social elites. And it was in this context that I wanted to explore the 1906 earthquake and how our ideas become embedded in the rock record. What did we know before the earthquake, and what did we learn in its aftermath? Well, in terms of 1906, it's actually much easier to talk about what we learned in the aftermath, because before, honestly, we didn't know that much. Keep in mind that to a geoscientist in 1906, the theory of plate tectonics, the fundamental mechanism by which we understand how the planet works, wouldn't be formally accepted for another 60 years. The earthquake struck at 5:12 in the morning on April 18th, 1906. The fault slipped 21 feet in a matter of seconds. And as it slipped, it sent out waves of energy, earthquake waves, that rippled out into the surrounding areas. Police Sergeant Jesse Cook was standing on Davis Street in San Francisco, and he watched the ground undulate beneath him. And he later wrote, it was as if the waves of the ocean were coming toward me, billowing as they came. Davis Street split open right in front of me. A gaping trench about 6 feet deep and half full of water suddenly yawned and sprang up on the sidewalk at the southeast corner, while the walls of the building I had marked for my asylum began tottering. Before I could get into the shelter of the doorway, the walls had actually fallen inward, but the stacked up cases of produce that filled the place prevented them from collapsing. Part of what makes the 1906 earthquake so important to a geoscientist like myself is that so many people made observations like this. They noted the time and the intensity of the shaking, and they documented the destruction using photography, which is a new concept in documenting earthquakes. In the years that followed the earthquake, a team of researchers gathered together to study the earthquake in greater detail than had ever been done before. And the team of researchers was led by this stud of a man, the head of the geology department at UC Berkeley, go Bears. His name was Andrew Lawson. And Lawson and his colleagues set out, again, to document the earthquake in greater detail than had ever been attempted before because they had access to much more information, a lot more data. So they began to conduct interviews with the survivors. They documented the destruction themselves, taking photographs. And they made countless measurements around the Bay Area and collected the only 92 seismographic readings of the earthquake, none of which came from the United States. So that was hard work in 1906. In the end, Lawson and his team produced a report, cleverly called the Lawson Report. And it totally revolutionized the burgeoning field of seismology. It was also a 400-page document that very few people read. But hidden in those pages, embedded in those changes, were the seeds of ideas that would ripple out and become embedded in the rock record. They began by just making observations. Lawson and his colleagues noted that the earthquake appeared to have started on the San Andreas Fault. And while that might sound obvious today, that wasn't known back then. In fact, in 1906, most people, geologists included, thought that earthquakes and all of the shaking created the fault, rather than the fault generating the earthquake. Lawson and his colleagues also noted that the fault had slipped horizontally rather than vertically. And again, while that seems like sort of a trivial observation, it slipped horizontally, at the time it was thought that earthquakes could only be generated by vertical motions. So with these two seemingly simple, deceptively simple observations, the Lawson Report is already radically transforming our understanding of the natural world and our relationship with it. Lawson also teamed up with a man named Grove Carl Gilbert, who is a legend to nerdy geologists like myself. And Lawson and Gilbert set out to map all 600 plus miles of the San Andreas Fault through California. Not an easy job in 1906, on foot and horseback through a lot of poison oak. But they ended up making that trace, and they ended up documenting, again, all of these motions along the fault, these deceptively simple observations. And while those are very important, perhaps the most revolutionary concept to be found in the Lawson Report belongs to this man, a geologist from Johns Hopkins University named Henry Fielding Reed. And Reed and his colleagues came out to the Bay Area very soon after the earthquake. And they began to make their own observations. And specifically, they were interested in how the landscape had changed, before and after the earthquake. And what Reed and his colleagues noted is that the fault didn't appear to have slipped the same amount everywhere. In fact, they saw that it had slipped a much greater distance where the earthquake epicenter was, and then as you moved away from that epicenter along the San Andreas Fault, it seemed to slip less and less and less and less, as though the crust itself were absorbing some of that motion, a little bit like a rubber band just sort of elastically absorbing something. This led Reed and his colleagues to propose a new theory on the working mechanics of earthquakes. They postulated that stress and strain would build up on a fault over time, a little bit like stretching out that rubber band, until eventually the friction on the fault could no longer hold and it would slip and generate an earthquake, the rubber band snapping back into place. This theory became known as elastic rebound theory. And to this day, it is still the best working hypothesis we have on the fundamentals of earthquakes. It's hard for me to convey just how revolutionary this report was and how important this report was to geosciences. Everything we take for granted has its origins here. The fact that we can drive down the coast to Montara Beach, and if you walk to the southern end of the beach, nestled into the cliff, you'll see a shape that looks like a V in the rocks. And next to it, you'll see a group of granite that doesn't belong there because granite belongs under mountain belts, and there are no mountains down there. Well, our knowledge that faults can slip horizontally led us to figure out that this granite came from Los Angeles and was transported up here over millions of years of horizontal motion on the faults. The fact that you can go out to a fence that once crossed the San Andreas Fault and in 1906 was offset by that near 20 feet, and that all of us would look at that without having me explained much of this. You would be able to look at that and say, oh yeah, that was probably an earthquake. Something slipped and that's what created that sort of motion. Those ideas, that intuition began here. And the very idea that we have to pay for pretty expensive retrofits for buildings also began here. We have to protect ourselves from these earthquake waves and these motions. In 1906, this was a big deal, and this is how our ideas began to imprint themselves into the rock record. We don't need to go through all of this history in a book anymore. You can go out, look at that offset fence, look at that V, look at the granite, and be able to intuit, plate tectonics, earthquakes, natural history is happening here. So we're now up to 1906, and I want to shift now to the present day, and we're going to turn now to Otto's beautiful drawing here. What Otto has drawn are the different shorelines that existed in the Bay Area going back 18,000 years all the way up to the present. And you can see the X is us here at the interval. And it's not hard to imagine that if the shoreline has changed this much, that it's going to continue to change. And certainly as humans play a bigger and bigger role in transforming the landscape. We've already seen examples of that. In fact, the idea of humans being a geological force capable of transforming landscapes has a name. It's called the Anthropocene. And I have a podcast all about it. You can ask me about it. The idea of the Anthropocene is that humans are a geologic force on par with plate tectonics, ice ages, things of that nature. And the idea that we're going to add a new chapter in the geologic timetable is a really big deal. It's like adding a new element to the periodic table. So this is a profound statement of who we are and what we're capable of. And given that, it's not hard to imagine at all that 100 years from now, 1,000 years from now, Otto would have to draw some really weird contours up here. But again, those are some of those physical changes and our ideas, what we want to preserve. And to end the talk, I didn't want to end in the modern day, in the Anthropocene. I actually wanted to go back in time once more. And specifically, I wanted to go back to the year 1792. In 1792, a captain by the name of George Vancouver became the first Englishman to ever set foot in San Francisco. And his ship parked in a bay, probably one that doesn't exist anymore. And he left the ship, walked onto the peninsula, and carried with him a journal. And in that journal, he began to keep copious notes. And fortunately for me, a lot of those notes were about the natural world he saw around him. When he stepped onto the peninsula, he wrote, "The plain is by no means a dead flat, but of uneven surface. The soil is of a sandy nature and was wholly under pasture, on which were grazing several flocks of sheep and herds of cattle. The sides of the surrounding hills, though but moderately elevated, seemed barren, and their summits were composed of naked, uneven rocks. 2 small spaces in the plain were appropriated to kitchen gardens. The several seeds once planted in the ground, nature was left to do the rest without receiving any assistance from manual labor." The nature that Vancouver was describing had already been radically transformed by humans, even in 1792. More recently by the Spanish missionaries, and then for millennia before that by the Native Americans. And again, a lot of those changes were physical, and a lot of those changes were ideas that became imprinted in that rock record. And I'll speak only for myself. If you've heard talks about these ideas of restoration biology or de-extinction, the idea of bringing extinct animals back to life, at the heart of these ideas are that we can somehow return nature to a pristine state before humans. And speaking only for myself, I'll say it's enticing. It's very easy to become nostalgic for this idea of a pristine nature or a pristine wilderness. But as we've seen through just tens of thousands of years here, that's also a nature that never really existed. There is no pristine. It's constantly changing. There is no baseline. But that doesn't mean that these layers disappear. If they did, I would have had a really hard time putting this talk together. When we read the rocks of San Francisco, we're not just reading our natural history, but we're seeing how the natural world and our relationship with the natural world has informed our culture. We've seen gold bring commerce. We've seen the bay and the harbor bring trade and the exchange of ideas. And we've seen the food bring pretentious Yelp reviews. When you know where to look for it, you can find this amazing amalgam of our personal history and our natural history written into our rocks. Thank you.
Excellent.
Thank you.
So everyone get your questions in mind. Rio, hold up your hand, hold up the mic. There's a microphone in the back with Rio, and Rio will look for her, and she will find you with the mic, and then I'll find her to get your question up here. We've got a lot of questions, I think, for here. And I also, again, want to mention the folks on the live stream. I understand we've got folks from as far as Michigan and Oregon tonight. Thanks for tuning in, folks. And you guys can add questions, too. Just put them in the chat, and I'll actually be able to see them up here on stage. So, Miles, so you wrote me in an email. We were talking about what it is you do for a living. Because, believe it or not, this is not the only thing he does. And you said, seafloor landscapes and their interactions with fluid mechanics processes. Is that about right? Can you do a slight translation of that for us?
Absolutely. So it turns out, and actually there's a great picture with Otto right up here that helps demonstrate this. It turns out that we have way, way better pictures of the surface of Mars than we do of our own seafloor. And our seafloor is remarkable. It's an absolutely alien environment. There are a lot of things happening down there that are very difficult to explain, and a lot of things that, in my opinion, are quite beautiful, and we have a lot of impact on, turns out. So if you remember when I was talking about ancient sea level rise in the river that cut across the slope when sea level was way out past the Farallon, or when the shoreline was out past the Farallons, well, you can see at contour number 2, it does this sort of weird pointy thing pointing back in towards the bay. And that little pointy thing is actually a canyon that's been carved into the slope in the submarine floor. And those are the types of things that I'm really interested in because, one, they're huge. In fact, if you go down to Monterey Bay, there's a canyon out there that's bigger than the Grand Canyon. And 2, we have no idea how they form. And I like answering those kinds of problems because no one can argue with me. I say it does this. Sure. But the cool thing from a human perspective in dealing with this is that, one, the flows that we think create these pose huge problems to man-made infrastructures, things like telegraph cables and internet cables and things like that run along the seafloor. And the second thing is that a lot of the stuff that we end up dumping into the rivers and the stuff that we use for agriculture will end up hundreds of miles offshore out in these deposits that are carried through these submarine canyons. And so actually, if you really want to record a really accurate signal of the Anthropocene, I argue that going out to these deep sea fans and getting a core out through there is one of the best ways to do that.
And how would characterize for us, because obviously you're here, you know this area really well. It seems like a fantastically interesting geologic area. Give us a sense of, I mean, are we uniquely like that, or is everywhere as interesting as this? I'm kind of, where would you rank the Bay Area geology?
Oh no, I'm about to offend so many people.
That's our goal here.
Yes,
right. Ruin your professional reputation.
I'm either going to alienate the room or the rest of the world. I will say that California, and specifically the Bay Area geology, is among the most complex that we know of. And it's very strange because there have been a lot of different things that have happened here, a lot that I've mentioned in the talk. And one of the weirdest things that happened that I didn't get a chance to talk about is that the Pacific Plate and the North American Plate used to be doing this, and now they're doing this. That's weird. And it's also a process that we don't really know all that much about. And so there's a lot of weirdness that's sort of built into the geology around here. And in terms of a human impact in the rock record, it works very well here because of a lot of the agriculture, because of the water, because of the bay, because we have a lot of things that settle very slowly and give us very clean layers that help us demarcate sort of geologic time. So I do think the Bay Area is sort of unique in that sense. But all geology is awesome. I mean, you can go to some really cool places and just have one rock type. I'll do a quick aside. So there's a weird rock type formation that's actually in central Texas. And in central Texas, most of the rocks that are there are all in the order of, maybe tens of millions of years old. The oldest you get is maybe 150 million years old, something like that. And then there's just this one sprig of rock out in the middle of nowhere that's like 650 million years old. Sure.
Whereabouts is that?
I think it's just west of central Texas. I don't know exactly what city it's near, because I'm pretty sure it's out in the middle of nowhere. But it's one of those really weird problems that people have been trying to figure out for quite some time.
All right, I think we got a question back there.
Thank you for your awesome description of how gold forms. I've always been curious, and I'm wondering if you've come across this. California seems to be one of the only places in the world where huge chunks of gold sat upon the surface with people walking by them for at least 10,000 years, and nobody cared about them. Everywhere else in the whole world, and it's at least that I know of, people really, really cared about it, and it became this precious object. And I'm wondering if you know of other places where that was the case, or if you've heard of any reasons why the California Native Americans decided they didn't care about gold.
Off the top of my head, the closest analogy that I would have to gold just being out in the open that people tended just to not care that much about would actually be in the Dakota Territories. And the Native Americans in the Dakota Territories also saw the gold and didn't care that much about it until it was discovered by, I believe, soldiers, but don't quote me on that bit of history. And when gold was discovered, the phrase, "there's gold in them thar hills," that was what that was referring to, was the Black Hills. And all of a sudden, something like, the city, for those of you who are fans of HBO's Deadwood, the city of Deadwood went from having a population of about maybe like 5,000 to a population of 40,000 in like 2 years. And that was just everyone going, "Gold! Oh my God, there's gold!" And that was where that gold rush sort of began. But I would guess that actually that idea of gold being precious is only a new thing. My hunch is that for most of human history, gold would be, "Oh, that's pretty, but I can't eat that."
Central America and South American Native Americans all had made gold precious objects.
That's right, yeah, and I don't know when it became something of, this is a precious object, this is something that means a lot to us, to I am willing to murder everyone to obtain that object. I'm sure there's somebody out there who knows the answer to that. I'm not that person.
Right there.
Can you talk a bit about how climate change is affecting geologic science?
Sure. So we're going to be here for a while. So
the
let me
theme
go
of the
through.
talk,
Yeah,
actually.
exactly. That's a whole other talk. But let me go through a couple of the quick versions of it. One of the big ones is that climate change is affecting agriculture hugely. And in order to make up for the warmer temperatures and the increased droughts, we're finding ourselves dumping more and more fertilizers. And those fertilizers end up in groundwater, they end up in surface runoff, they end up in rivers, and then they end up depositing out in the oceans. And so you get these huge chemical signatures, and that's one way that climate change is affecting the hard rock sort of geology. Another big way is through ocean acidification. As carbon dioxide goes up into the air, a lot of that gets absorbed by seawater. When you take carbon dioxide and dissolve it in seawater, it becomes carbonic acid. And that acid begins to eat away at coral reefs, and those reefs disappear from the rock record. They're called reef gaps. And we've seen them at various times in Earth history, and we're almost certainly going to see that in the near future. So that's another sort of very tangible way that we're going to see climate change affecting the rock record. Then there's some other weirder ways that I won't dive super into because it involves a lot of geochemistry that gets, again, that'd be a whole other talk to sort of go through that. But with climate change, there's a natural cycle to how carbon is released and reabsorbed by the planet. And climate change is messing with that largely through what's called weathering, chemical weathering. And it's basically just a fancy way of saying rain falls on rock, the rock changes its chemical shape, and as a result of undergoing a chemical change, it absorbs carbon dioxide or releases carbon dioxide. And those signals are changing. So those are a couple of different ways that climate change is actually affecting the hard rock sort of history of the planet right now.
Anything specific to the Bay Area?
In the Bay Area, there are, the clearest signal is going to be the agricultural signal. And you've seen that in the last couple of years until very recently when El Nino came in and helped us. Didn't make everything better, but El Nino certainly helped us get through this huge extended period of drought. And that drought is something that you can read not only in the rock record, and you see the layers of changing thickness of rock, but you can also see that in tree rings. You can see how the trees will change their growth rates, and those trees will also get preserved sometimes, if we're lucky, in the rock record.
And I should say quickly that, because I think we'll have more questions than you can answer, but then you have more answers than we can question. So Miles is going to stick around, so please do stick around also and continue to ask him questions. A quick follow-up on that question. Can you say something about how scientists in different disciplines are collaborating? Because obviously geology is the best, but their effects on biology, their effects on animals and plant systems. Can you say something about how, say, the data you're doing gets used? What other scientists are collaborating with you, especially on the climate change side?
Sure. So, the sort of name of the game, this happened a little bit in the late 1990s, early 2000s. There was a major shift in earth sciences, and it stopped being I'm a geologist, I'm a biologist, I'm a geophysicist. That stopped really being a thing. And what shifted was this idea that became known as an Earth systems approach. And Earth systems means basically what it sounds like. The idea that geology is separate from biology. Why? It's just not true. And so it involved building way more complicated models, which was fortunate because now we had way more powerful computers to start dealing with those kinds of problems. And so a very micro example that's also kind of, I think, a humorous example of people collaborating across a lot of different disciplines. In landscape evolution, there are a lot of models for how landscapes will evolve, how erosion basically occurs. And it used to be we would look at things like rainfall, rivers, done. And that was kind of what we would look at. And now when you have those same models, it's not just the sort of physical processes, the physics-based stuff, but there's also equations where the terms in the equation are, I kid you not, humans and gophers. Because it turns out gophers can dig up so much material that they themselves will transform the landscape. And that's a biological reveal that we never would have thrown into a geological model before. But these are some examples of ways that collaboration works.
Gopherocene?
Yeah,
Is that what we're...
I don't think they're that dominant. Maybe, I don't know.
We have another question over here. There we go.
So you mentioned when the California Valley was being formed, that was scraping off the top layer of another plate, which previously had been under what you called a shallow ocean.
That's right.
how shallow is a shallow ocean compared to what I would think of as like the Pacific Ocean today, and why was that shallower than other oceans?
Okay, once again, this is like a whole talk, but we'll go through it briefly. So, short version. The depth of the ocean is in large part dependent on the density of the crust. And so because basalt, which is what ocean crust is made of, is very dense, and granite actually isn't. Granite is pretty buoyant, and granite is basically what most continents are made out of. The continents tend to rise up, and the basalt tends to sink down, and that's what will create the topography difference that eventually becomes the ocean depth. So that's basic Oceans 101, but it gets more complicated than that. So the reason it was buried under a shallow ocean and not a deep ocean is because there's a shelf that runs out along the coastline. In fact, that one contour line there, that's basically where the continental shelf is. And that the location of that line is, again, largely dependent on the chemical composition, the actual mineral composition of the crust, whether it's all basalt or all granite. Spoiler alert, there's really no such thing as all of any one type of rock. But it's usually some sort of a difference. And so you'll eventually find this place where the crust is like, I can be buoyant. No, I can't. And it falls off. And that, I mean, I'm grossly oversimplifying this, but that's basically where that line shows up. And so what ends up happening is that you have this buoyant crust over here, this dense crust over here, and then you have sort of a shallow depth, a shallow falling off, and then a steep drop off, and then it just falls flat because the most of the planet is made up of this basalt that just sits way, way low down and to create the deep ocean. So that's where the shallow ocean comes from. And it wasn't all one depth. It was gradually getting deeper as you move to the west, but it was still much shallower than, the Marianas Trench is way, 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 way deeper than what was there.
Can't believe you ruined that basalt thing for everybody.
I'm that guy now.
And as I said, you'll be able to talk about more things afterwards. But I want to get in quickly before you get another audience question. The Game of Thrones thing. Now, this was something that just came straight out of your head, right? Is that right? You would just tell us how the light bulb went off, or how you got obsessed with this.
So the short version is that using my knowledge of geology and geological history, I was able to go through the Game of Thrones books, the TV show, and I'll say too many other websites, to build a 500 million year plus geological history of the Game of Thrones planet, which you can see in that colorful map in the middle there. And the project began with me sitting around with a friend of mine, and we're big pop culture fans, we're big Game of Thrones fans, and he's a climate scientist. My friend's a climate scientist. And he was wondering about how in the Game of Thrones universe, seasons make no sense. Like all of a sudden it's winter for 2 years, and then it's summer for 3 months, and then it's winter for 2 weeks, and then it's summer for 5 years. And it just made no sense. And there have been a lot of people who have actually run like physical models, physics-based models to try to figure out how this works. Short answer, it doesn't. And so my friend's hypothesis was, wait a minute, fire, burning stuff changes climate. Fire can change climate rapidly. What if it was dragon's fire that was changing the climate really quickly? And rather than laugh, I thought I could calculate that. And that's where that came from.
And so there are plot twists that you're getting, like in the weather patterns, that we're not even appreciating.
Totally.
I guess.
Also, there's a really fun moment for those who are Game of Thrones aficionados, and even if you're not, if you just want to dive into the geology, I go through and explain sort of like similar to this, contour by contour, geologic.
This isn't just a
period by
blog
geologic
post, right?
period.
You've got a
It's
bunch of
pages of stuff.
And pages.
It's a great read. And you can sort of dive into all of this history. And one of the things that was really interesting is that I was trying my best to make things work, and they worked surprisingly well. Like that was the shocking part to me. And I finished it and I was like, good, here it is. And I put it out. And then another friend of mine, who's also a climate scientist, was like, wait a minute. when did you say the last big ice age was? And I went through my calculations, and he went, okay. And what are the elevations of those mountains? And I said, here are the elevations of those mountains. And he was like, okay. Wait, and what's the size? And I was like, dude, what are you doing? And he's like, oh, I'm plugging them into my model right now. And he actually was going through to see if the rise of these mountains that I had timed in just in a geological background would match the climate patterns. And spoiler alert, they matched. And I was like, wow, that's awesome. So it turns out science works.
Science. We got a question up front here.
Yeah.
Yeah, you're good.
Hello?
Just hold it close. You'll be good.
Like Barry, right? Okay, so my first question is, and I know the answer is it depends, but on average, just how thick is the Earth's crust that's floating above the mantle? And then the second question is, what effect does that have on plate tectonics and movement? And you know, for instance, like, why no super big ass earthquakes in the Himalayas? You get what I'm saying?
Totally. Once again,
Is the answer geology?
the answer is, of course, geology. Right. Great, I have you all queued up now. This is awesome. So you're right. The answer is, of course, it depends. But weirdly, it only really depends if you're on a continent or if you're on the ocean. Most ocean crust tends to be about the same thickness, and this is where I'm going to enrage certain geologists, because the crust is actually, it's a hard term to define. It's a little bit like saying planet. You know, the idea that Earth and Jupiter are somehow in the same class just doesn't make a lot of sense. And the crust of Earth, there's not like, there it is, there's the bottom. It's actually much more difficult to define than that. But generally speaking, oceanic crust is about maybe 10 miles thick, give or take. And under a continent, it can be 30-ish, 35 miles thick. And again, I'm enraging certain geologists who are going to be like, oh my God, those numbers are way too small. But generally speaking, that's about what it is. And so in terms of plate motions and how that works into plate tectonics, again, this is primarily actually density driven. So because you have basalt, which is that ocean crust that's much thinner, so you get this mantle upwelling. And mantle is very, very hot. And especially the stuff that's coming up from deeper. The deeper you go, the hotter it gets. And so as it comes up to the surface, it hits the crust, and it wants to keep going, but it can't go up anymore, so it starts to go in different directions, right, convection cells. And so it basically creates a conveyor belt. And when the basalt, which is much denser, begins to get basically translated over on this conveyor belt, and it hits the continental crust, and then it goes like, oh, crap, well, I can't go any farther. Well, I'm denser than the other one. So it drops down, and it starts to sink down underneath it because it's much colder at this point. And so it begins to fall under, and then it melts. And as it melts, a lot of the water boils off, and it creates a lot of volatiles. That's where volcanoes come from. That's where you get the ring of fire around the Pacific Ocean. But it's not so much the thickness that helps drive the plate motions. It's the density differences in between them. And then the reasons that you get really big earthquakes in some regions and not in others is if you imagine that the crust is only this thick, and we'll just say that it's 10 miles thick, and if you draw a fault through it that's straight vertical, you don't have a lot of surface area. But if you cut it at a really shallow angle, you now have a lot of surface area, and so you can build up a lot of friction. Well, those shallow subduction areas don't exist everywhere in the world. And you can get big earthquakes on steeply dipping faults, but the really, really big earthquakes, the ones that in 2001 created the huge tsunami in Sumatra, Japan, the mega earthquake that happened there, those happen because of a combination of things. One, because there was a lot of surface area to hold on to that friction. And the second is that those plates are hauling ass, geologically speaking. I mean, this is like, yeah. Look, when I hear centimeters
Could someone put
per
that on
year,
Twitter, please?
Oh my God. So that's where they go.
A quick follow-up on that. Do we know, do we understand what all the plates are? Where those, are we deducing based on previous seismic activity? Or do we actually know all the places that have that type of configuration, that potential?
We know the configurations for the big earthquakes, for the most part. one of the reasons that the Tohoku earthquake was such a big surprise, the one that happened in Japan. It was such a big surprise because all of the models that had been applied previously turned out to be wrong. And they had suggested that fault, or the strain on that fault couldn't build up in the way that it did. And that was just turns out to be wrong observations. People were interpreting the observations incorrectly. It's a more appropriate way of saying that. So we know those plate configurations reasonably well of where those big earthquakes are going to happen. But one of the most interesting questions that's hidden in what you just asked is, do we know where all of the plate boundaries are? And the answer is no. One of the most interesting things that's happening right now, at least interesting to me personally, is there's an area in Eastern Africa. It's called the East African Rift. And it runs a lot through Kenya. And the African continent's actually starting to sort of split apart. And there's debate, and I wouldn't say it's healthy debate, but there is some level of debate if we're watching the birth of a new tectonic plate. There would be no precedent for this. We've never seen it on human timescales because tectonics takes a really long time to work. But that might be a boundary that we're still trying to figure out a little bit. There's a lot of micro-tectonics in the West Pacific that don't make a lot of sense, but we have a fairly good idea. But the great mystery right now, if you're looking for a fundamental problem in geology, if you want to dive into it, where are the plate boundaries in the Arctic? We have no idea. In fact, the motions of the plates when we get up that far are really difficult to constrain. One, because GPS satellites tend not to orbit the Arctic, so you can't get really, really accurate measurements, but also because it's all ice flow. I'm gonna set up a GPS station. It just keeps drifting. And so you can't actually make a good measurement. And so it's very, very difficult to figure out how things are moving. And then also you have the huge ice sheet, which is melting rapidly. So maybe we'll be able to figure it out soon. And you can actually go down and see a little bit more, like image the seafloor and try to figure out where exactly the plate boundaries are snaking around up there.
So we're about to wrap up, and like I said, he's going to stick around. Some keywords to ask him about are, what was the time period when all the fossil fuels arrived, which is pretty much, yeah, so that's one thing. The carbon footprint of superheroes, more about Game of Thrones. There are lots of things to ask him about. Please stay around and do that. I have one last question, and as I said, we're right up at the end. So this is fun. This is a great talk. It's really fun. We've all learned a lot. We've been entertained. Say something for a second about what's important about connecting science to pop culture, being entertaining about it. I don't know. I mean, because obviously you enjoy this, and it's your nerdery that you're following around to your nerd instincts to do it.
Yep.
But is it important to scientists, to other scientists? Is it helping to make things happen? Can you just say something about, because obviously it's part of your approach to science.
Sure. I'm biased, but yeah, of course it's important. It's important for a lot of different reasons. Science has for too long been portrayed as something that only sits in this lofty realm of experts sitting, up in the clouds doing things that we can't possibly do. And that's crap. We can all do this. It takes a lot of time, and you have to learn a lot, and you have to stick with it, and you have to have a lot of perseverance. And through that process of learning a lot of these materials, you find different ways of teaching it, of making it interesting, of making it engaging. And that's where it's really important, and I will argue for even fellow scientists to sort of show how to make their work more approachable to the rest of the world. It was one of the things that inspired the Carbon Footprint of Superheroes project, is that climate change is unquestionably one of the biggest problems that we've ever faced. And yet, here's a room of very intelligent people. If I asked all of you, if I said my carbon footprint is 44,000 pounds per year, is that number good or bad? Exactly. It's a hard question. And we hear these ideas and we have these numbers and these concepts, but they don't mean anything to us at a really deep sort of level. But when you can attach that to something that people already have maybe too much meaning in, like Game of Thrones or superheroes, I'm speaking only for myself. I've invested a lot in these two worlds. But when you invest, when you bring more meaning to that, that makes people, makes it much easier for people to draw the parallels to their own lives. That's at the heart of these projects, and that's why I think you have to be entertaining. You have to try to link this stuff to popular culture and the things that we experience in our everyday lives much more frequently. However, we want to say that's good or bad. That's just what's true. We experience these things way more frequently than we do a geology textbook or a lesson of the 1906 earthquake. So that's why it's important.
Miles Traer, everybody.
Thank you.